Okay. Good morning, everybody, and welcome. It's so nice to see all of you here. So today we're into chapter 3, which is on forces. And one of the forces we're going to be talking about quite a lot is gravity. And I've noticed these signs all over University of Toronto. Apparently it's our slogan, which is Defy Gravity. So I feel like that angry guy on this crazy guy in his front lawn saying, "Don't defy gravity." I always picture like someone going to the edge of a cliff and going, "Gravity, I defy you," and going off. "Ah, I shouldn't have defied gravity." Splat. Something. And then of course there's Calvin and Hobbes. He's looking at a helium balloon, and you release a helium balloon. And as things do, it falls down, right? No, it falls up. It's like, okay, that's it. Forget it. So I want to introduce you to Nemo, our fish here that Pius has brought in, who is the helium-filled fish. And he's got a tail so he can flap around. He's a little shy today. He's getting caught in the currents. So the way he flies is that basically he just flaps his back fin there, and that's all he needs to do. Look at him going in there. Come on. We're going to see if he can pick up any altitude and get him up to the balcony. That's my goal. If you can get him to the balcony, that'd be amazing. He's got a little ballast which moves back and forth to kind of steer him. Anyway, so this is about buoyancy force, which you can search up on section 13.5, which is that if an object is immersed in a fluid, here on Earth, like the fluid here being the air, then there is an upward force on that object equal in magnitude to the weight of the fluid that's being displaced. And so for most of us, that's a negligible force, right? Because we are pretty massive compared to the amount of air that we displace. But it's forcing us upwards. And for an object like a helium balloon, he's left the room, but he may come back. The object is so light that it's actually lighter than the amount of air that has been displaced by its volume, and so it goes up. So there you go. It's not gravity's not arbitrary either. Okay. I wanted to let you know tonight also that this is an online event. It's a panel discussion on dark matter and metaphor. These are three of my friends here, actually. Professor Lochik from astronomy, Professor Curtin, and Professor Diamond are particle physicists. So Professor Curtin's more like a theorist, and Professor Diamond is experimentalist, works at Snow Lab on neutrinos and dark matter. Anyway, there's the link. It's U of T Me 8IE. You can click on that. You have to register to get the Zoom link, but it's free. So if you have time, you can check that out. Also, just not to be a downer, but yeah, so outside of class time, we have this midterm coming up on Tuesday. There's another Tuesday further into November, but October 11th, we're all going to gather down at what's called the Examination Center, 255 McCall Street. I have many more details about how to get there and all that, and we're going to write a midterm for about an hour and a half. Took you 80 minutes. And it's on chapters 1 through 4, plus the stuff that you're doing in practicals this week and next week. And then the third week of practicals, which is just the one before this, we're going to go through kind of a practice test. There'll be 10 multiple choice questions, plus a written question you have to write out, and someone's going to read it and mark it. And I've got a good question from the front row. If you use different symbols or something for the kinematics equations I showed, that's fine, as long as you carefully show all your reasoning and explain what you're doing. The person who's marking it will be a PhD student in physics and will be able to figure it out if you use slightly different notation. But you got to show your steps. Yeah, so the practice, the warm-up midterm is going to look very similar to the real midterm, and so you kind of get used to it. It'll have 10 multiple choice, it'll have a written answer problem, but in that one you're allowed to work together and talk and go to the whiteboard, and in fact, you're encouraged to try to talk through these things. And if you have a time conflict, there's an alternate sitting. This is just before, so you can register for that. And that will end by 6 and get you out of there if you have a 6 o'clock class on Tuesdays. Okay. All right, so forces. Okay, so kinematics is the study of just sort of how things move, but dynamics, which is what we're getting into in chapter 3, is the study of why things move. And this is beginning to get into things like force, energy, momentum, and all that stuff. I don't know where the fish is. So here's a thought experiment, and it's James Bond is standing still in the middle of an ice-covered lake. If the surface and somehow the bottoms of his shoes were both perfectly slippery, would he be able to walk away? And the answer is, surprisingly, no. Okay? You need an external, unbalanced force. There is a force on him of gravity, but that's going to be balanced by the upward force from the lake. You need an external, unbalanced force is needed to accelerate an object. So if he starts at rest and wants to accelerate, the object being James Bond here, then some force has to be on him. Maybe somebody might throw him a rope. But this is, believe it or not, how we walk. Is the steps are, I press to the left with my feet on the floor, then the floor presses to the right on me with an equal and opposite force, and I accelerate towards the right. Seems a bit convoluted, but that's the idea. And it is, in both cases, it's the friction force between the bottoms of my feet and the carpet, which is the external force which accelerates me on this surface. So if it was really slippery, I would just kind of like go like that, and I would just fall down. It'd be like standing on marbles or something. So we're getting into Newton's laws here. The way it is introduced in your textbook is it talks about this system. And it is actually really useful to kind of define your system. A system is the object or group of objects that we choose to analyze. And sometimes we draw a little dashed line around the system. And we can label it system. In this case, it's James Bond. And so everything outside that system is called the environment. So, for example, the surface of the lake is an environment, and that pushes upwards. So I'll just say right here, the surface of the lake pushes upward on the system, as we've defined it, which is James Bond. And then there's actually another, there's also the gravity. It's a long-range force. Gravity pulls down on the system. So these are the two forces that I was going to say that they cancel out each other. Is gravity is pulling down, the lake is pushing up. Those are, if they're equal and opposite, they'll cancel. And then maybe a rope. So here is, and again, another thing, the environment. Remember, his shoes are perfectly slippery, so the only way that he can get rescued is for someone to pull him with a rope, and that can produce a force to the right on that system. So, what is a force? Let's go through a couple of slides. Again, you've read about this from chapter 3, so I'll go through it a little bit quickly, and then we'll do some demonstrations and some learning catalytics questions today. A force is a physical quantity that characterizes how hard and in what direction an external object pushes or pulls on the system. So there's a javelin, and maybe the javelin is the system, and the javelin thrower is the environment that then accelerates the javelin. So we say that there's an external force acting on the system. It could be a push or a pull. From the system's perspective, maybe the javelin in this case, there is an external force acted on it. So you could have a contact force, like pushing something, call that a normal force, or you can have sometimes a long-range force, like gravity, that just sort of reaches out and grabs something, even though it's not touching. Somehow Earth pulls on the tennis ball without touching it. And I guess magnets do that too. You have a long-range force between magnets sometimes. There's a unit, just as there's the unit of length is meter, the unit of time is second. The SI unit, or System International unit for force, is called the Newton. And then if you're going to draw force vectors, one way of doing it is you can represent the system or the object the force is acting on as the tail of the vector, and then draw the force vector acting away from that. And that's the way I like to draw force vectors. Sometimes you see them going towards I guess, the head at the object, but in this book, and for me, I like to draw it going away, just easier. Okay. So there's something called a force diagram, sometimes called a free body diagram, and this is a very important first step whenever you're trying to solve problems in Chapter 3 or Chapter 4, which is draw a force diagram. So you have an object, try to draw all the forces that are acting on the object, and these are all external forces from something else. So we'll take this James Bond guy as an example. We represent the system by a dot. So let's draw, maybe I'll use black to put a dot right here. That's James Bond. And then the arrow represents the forces. So what we're going to do is try to think, here, remember, here's the system. System equals bond, B, I guess. This is the rope. Maybe I'll call that R for rope. And let's draw the force diagram with arrows. So since I have colors, I might as well use red. So there's going to be this force, for example, of the rope on bond. So I'm going to use subscripts to show which one's the environment. So the environment first, acting on the object. And there's other forces, which might be this one, the force of the lake on bond, upward force. L equals the lake surface, I guess. And then there's another force, which is the same magnitude as FL on B, called FE on B. You'll never guess what the E stands for. It's not energy. Does anybody have a guess? Earth, thank you. Okay, that's a tricky one. E stands for the Earth. And what that means is, once again, there is some force reaching out from the whole Earth on bond. It's not a contact force, and it's pulling down on every particle in his body, and then you kind of represent that in the force diagram just with that one arrow. So thanks for that. And that's the force diagram. I can't think of any other important forces on him at that moment. And so there's going to be an unbalanced force, which I think in this case is going to accelerate him towards the right. Okay. All right, so let's go through a couple more slides here. So this is a situation from your textbook. This is Toolbox 3.1, and the situation is a little hard to picture. It's a rock sinking into sand, meaning that it fell, it hit the sand, and is now slowing down to a stop. So normally you kind of think of something hitting the ground and stopping immediately. Well, in this case, it's a pile of sand. So it hits the sand and then slows down as it's going. And so they're trying to think about what are the forces while that rock is sinking into the sand. So first you circle the system, which is the rock. And 3, you identify the external interactions. Well, you got the sand pushing upwards, and you got the earth pulling down with gravity. And since it's moving downwards, but slowing down, that means the acceleration is opposite the velocity, it's upwards. That's the tricky part. So what that means is that the upward force of the sand at this moment is greater than the downward force of gravity. So it gives it an acceleration upwards which combined with its velocity downwards means it's slowing down. I don't know why they put such a tricky example, but there you go. So that's why they drew that force of the sand on the rock as being a greater force than the force of the earth on the rock downwards. And it's important to remember that on a force diagram, you only draw forces that are exerted on the object. And so maybe if we go back to that bond one for a little bit, notice that they're all on B, on B, on B, because B is the system. And it seems a little repetitive, but it reminds me that you can put them on the force diagram if it's the force diagram of bond, right? Do not draw forces that the system exerts on the other objects. That's a common mistake. As you think about him pushing down, that's an upward force because the surface is pushing upward on bond. Okay. And then there's something called the net force, which in this book is always drawn with this sigma letter. Sigma means, in this case, the sum of. It's of the forces. Sigma F means the sum of all the forces. And since the forces are represented with a vector, it's actually the vector sum of all the forces. So you see this sigma coming up a lot in this book, and it always just means like the net force. Sigma F is the net force. So the sum of forces, source vectors, it's not a new force, this net force, it's just the sum. It's a combined effect of all the forces being exerted on the system. And because of this, you don't include that result on your force diagram. Sometimes it's useful, so sometimes I draw it to the side. But all the forces on the force diagram are just actual forces acting on it. So going back to that, well, here, it's like the sand one, but if you're accelerating this box upwards, there's u, y is u, and pulling upwards on the system, which is the box, then the net force is up, but this is the force diagram. You just draw those two, and you can sum them as being up. And let's do the bowling ball experiments. There's 3 of them. You may have seen them talking about it. So the first experiment is what happens if there's no force on the bowling ball. So first I've got it rolling. Boom. Well, it just goes along at, well, it's slowing down a bit. So there must be a friction force. But maybe somewhere over some time when friction's not that important, what you'll see is a constant velocity, approximately constant velocity. So with equally spaced dots in the motion diagram or something like that. Experiment 2 is that it gets rolling. Hey, Pius, do you want to maybe bowl this towards me, and then I'll try to slow it down? You bowl, and I'll stand here and try to prevent it from rolling using this stick. Good? Whoop, ah. So I can slow it down. Okay. So what I did is I exerted a force which is to the left, opposite the direction the ball was already rolling, and this is experiment 2, by the way. A constant net force produces an acceleration in the direction of that net force. So the net force was to the left, so I made it, the velocity was to the right, so I made it slow down. You can also make it speed up by just pushing to the right. So it gets faster and faster and faster as I continue pressing it with this thing until it goes off the edge and I destroy the bowling ball. Okay, so that was experiment 3, which is that I'm pushing towards the right, lightly on it. That's my little force from my meter stick. And the velocity gets bigger and bigger as it's speeding up, because velocity and acceleration are in the same direction. Great. This is the warning label. We're going to do Newton's laws in a minute. And Newton's laws should only be applied in inertial reference frames. This will come up a little later. An inertial reference frame is kind of like Convocation Hall, this room we're in, which is that I could make a X, Y, Z axis or something here, and it would not accelerate. The room's not accelerating. Okay. All right, you guys are probably ready to do something, right? Let us deliver. You toss a ball straight up into the air. So hopefully you can see this. There's a session ID on the screens. And this is the trick, you have to imagine the ball while it's flying on the upward trajectory. So after it leaves my hand, but before it gets to the top of its trajectory. So I can throw it like this. Now, on its way up, what are all of the forces, important forces that are acting on the ball? And I put there, do not neglect air resistance. Let you choose. There may be more than one force. Okay, so I think this, hopefully learning catalytics allows you to check more than one thingy on this. Darn it. So everyone is telling me that you cannot select more than one. So maybe we should just neglect air resistance. All right. That's too bad. Is anyone allowed to select more than one? Nobody? Well, that sucks, man. Okay, well, I'm going to leave that on and just tell you what I think the answer is. So that was a failure of many answers. So while it's flying, there is a downward force of gravity from the Earth. That's what's slowing it down. There is also a small downward drag force from air resistance, which is also pulling it down. But there is no upward force from my hand, and there is no upward inertial force carrying the ball forward along its trajectory. No and no. So my question is, then, how does it know to go up? While it's on its upward trajectory, I'm saying that there's no upward forces on it. So then why does it go up? Even the bowling ball, after Pius bowled it, it was going along to the right. And I would argue that after he let it go, there's no forces pushing it to the right. And yet, off it goes. So that's Newton's first law of motion. So, which is that for an observer that's in an inertial reference frame, when the net force on an object is 0, then the object either stays at rest or continues at a constant velocity in a straight line. And they don't say that here because velocity includes direction, but I'll just say ... in a straight line. Multiple choice. Let me just see here. Many choice. I think this next one might work. Let's try it. I think I just set the question up wrong. So let's deliver this one. So choose all of the following items that have a net force acting on them. A car moving on a curved road at a steady 50 kilometers an hour. B, a car moving on a straight road at a steady 100 kilometers per hour. C, a golf ball at the peak of its flight through the air. Or D, a rock falling off a cliff. Yeah, that's a good question. But I mean a non-zero net force. Okay. You guys want to click into this one? And then click all the ones you think apply. And I'll show you what people are answering. I think I set this question up properly, but I'm not sure how it's marked. Going once? Going twice? And we'll see what. So, yeah, pretty good. A lot of people realize that B is a zero net force. And then C was sort of the most controversial one. So let me just go through what my reasoning was, which is that if it's a curved road, for example, that means that's not a straight line. So you need some friction or something, some external unbalanced force, net force, in order to get a car to turn. And I guess if the road was perfectly slippery and there was no net force, you would go in a straight line right into the ditch. This one has a zero net force, constant velocity. Okay, so there may be forces on it, but they must all sum to zero in order to keep it going on a straight line at a constant velocity. Constant velocity implies zero net force. That's kind of Newton's first law. Golf ball at the peak of its flight through the air, I would say you've got gravity acting on both these, giving it this downward acceleration. And so in both of those cases, I mean, the golf ball is kind of going curving or something. If something's even going straight up, like that tennis ball, even at the top of its path, where it's at zero velocity, there's still gravity acting on it, so it's still accelerating. We talked about that with kinematics last time, is that something can be stopped, but still be accelerating. Okay. All right, so where's my phone? I know where my phone is. It's over there. So what I wanted to do next, and this is, again, I'm going to ask you to stand up. So apparently Athena has like 4 hours of Con Hall classes in a row here, and so I want everyone to stand up. And also I wanted to test this idea that the wave has zero acceleration, which we assumed. So I want to repeat the experiment of the wave. I guess we'll start over here and do the wave again with standing up, saying whoa, and sitting down. So, and remember, the most important thing is not to step on anybody's laptop. That's important, okay? I have wide angle mode on my iPhone, which can pretty much see everybody. It's really good. So I'm going to set it up, and then what we're going to do is after class, I'm going to load the video into tracker software, identify the center of the wave, and make graphs of position, velocity, and acceleration versus time. That's this software. So I will start it, load it in. Are we kind of ready? I'll cut out the first little bit while we set it up. But I'm going to go over there and I count 1, 2, 3, go. Then we're going to try the wave, and then I'll try to identify it, and we'll see, does it accelerate or not? Okay. Ready? 1, 2, 3, go. All right, thank you, thank you. So I don't know how I'm going to, so part of the first trick of tracker software is you have to click with your mouse, you right shift and press shift, click with your mouse to identify the center of the object. And I think that's going to be my trickiest part, but we'll see. I'll tell you on Friday. Okay. How is time doing here? We're doing great. Okay. So what is mass? So why am I asking you this question? I'm about to do Newton's second law, the F equals ma. So before we do that, F equals ma. So I want you to we've just spent weeks and weeks learning about the A. Today we've just introduced the F. And so the other variable in that equation is mass, m. What is mass? So mass is a scalar quantity. It's not a vector, unlike force and acceleration. And it describes an object's inertia. So what does that mean? Well, if something moves, it has the tendency to keep moving, or if it's staying still, it has a tendency to remain at rest. So we call that inertia. This ball has a lot of inertia. So I was to put it on the ground, for example, and give it a little tap with my external force, but if I do that for the lower mass object, boom, it starts accelerating, okay, and goes off. And I have to really push this thing to get it going, because this has a lot of mass, has a lot of inertia. I sort of use those two words interchangeably. It's an intrinsic property of the object. It actually is related to how many protons, neutrons, and electrons are sitting in that object. So it's a conserved property. You could, I guess, remove parts. You could break it in half, and each half would have half the mass or something. But you can't create mass or destroy it. And so when She-Hulk goes from someone who looks like this is about 50 kilograms or something, and then suddenly turns into someone who's like 150 kilograms, that's just wrong. You can't change your mass. So I think that maybe She-Hulk is less dense when she grows to that big size. I don't know what happens there, but I'm trying to figure that out. But it tells us something about the object regardless of what is happening to it. So this bowling ball, if you move it to the moon, would have the same mass. So here is Newton's second law, and you may have seen this written this way, F equals ma, and that's fine. It's just a rearrangement of that. And to be more careful, we should put arrows on the A and the F, because those are vector quantities. And we should put the little sum sign in front of the F to remind us that it's the net force. So for example, if you have a cart with a fan on it, then there might be some net force acting on it, which would accelerate it. So, and I like it actually in this form because it sort of tells you what's going on. You've got a fraction where if the numerator increases, it gets bigger. If the denominator increases, it gets less. So acceleration is like proportional to the force. Bigger force for the same mass is going to accelerate it more. But mass is on the bottom, so bigger mass for the same force, it'll accelerate less. Okay. So let's do another quiz. So this is another one which I made on learning catalytics. So I have no idea if it's going to work. Can you see it? You're supposed to draw the net force using your finger or something. It's another one of Jason's little learning catalytics experiments, and I'll just wander around and see if it seems to be working. You're supposed to draw the direction that the object accelerates in, which is the same as the direction of the net force, right? So, okay. Okay. Hopefully that works. I think where you click is just going to be like the head of the arrow, and it always, I set it up to connect always at the box. And should we cut it off? I can show you what my screen looks like right now. It's kind of funny. Going once, going twice. I'm gonna stop and laptop 2. Looks kind of like that. So I do sort of like the idea down and to the left. So the downward force more than compensates for the upward force. So there's some downward, but it's also going to the left, so you should drop a diagonal. And I kind of put it there, but I'll show you basic idea. Left and down, yeah. I guess so. It looks sort of like this. There's a few different ways of doing it. One way is you can use parallelogram rule to find F1 plus F2. And then you could combine F1 plus F2, again, parallelogram with F3. Kind of get it going like that. So that's the net force. And point being, acceleration is the same direction as F net. And here you're adding 3 vectors to get one final component. So I usually just pick 2, add those, and then add that sum to the third one. Okay, that's great. And time. Okay, I think I actually have another. Oh my God. Do another one here? Yeah. Okay. Question 4. This is just a regular multiple choice. There's only one correct answer here, I think. You are in a plane which is accelerating forward on a runway, and some careless person has left a tennis ball in the aisle. And what happens is that as the plane's taking off and you're going forward, the tennis ball starts to accelerate towards the back of the plane. Can you picture that? Makes sense, right? You're getting pushed into your chair, so things that are not buckled in are going to kind of fly to the back of the plane. So, according to Newton's second law, the observed acceleration indicates that there must be a net force on the tennis ball directed towards the back of the plane. So, which one is it? Is it air resistance? B, the plane must be at an angle, so the component of gravity is rolling down towards the back of the plane. C, the inertial force. D, the normal force. Or E, Newton's second law is not valid in your reference frame. Maybe discuss with your neighbor. Pick one of those, please. Okay, this may be more of a semantics question than a real physics question, but I have an answer in my mind. Semantics meaning it's what you call it that is important here, right? Going once, going twice, and stop. Let's see what I am seeing. Looks something like this. So, 31% of you voted for the inertial force, and 53% of you voted for Newton's second law is not valid in your reference frame. So again, I have some definite empathy for this one, but basically this is not a term used in this textbook. Or in this course. I don't talk about inertial force. I don't really know what it is. I can kind of get what it must be. It's like a fictitious force. It's that force that pushes you towards the back of the plane. And so what I'm saying is that there is no force pushing you towards the back of the plane. What is going on is you are not in an inertial reference frame. Your plane environment is accelerating towards the right. And so, if you're going to stay in that reference frame and not seem to fly backwards, then you're going to need a force pushing you forward. And that is why you feel the back of your seat pushing forward on you. It's to accelerate you, to keep you in this reference frame of the plane. So there's no backwards force on you at all. And why does the ball roll backward? Well, actually it didn't. The ball just stayed there, and the plane and you accelerated away from it. So you've got it all mixed up. It looks like the ball's rolling backwards, but if anything, it's probably going forwards due to a little bit of friction on it. It's your reference frame that's the problem here. There's no extra force pushing things backwards. Those are called fictitious forces. Okay? And this is going to come up again and again, especially when we get into like circular motion. There's going to be this fictitious centrifugal force which pulls you towards the outside of the curve, which biologists don't really think it's all that fictitious. You put a test tube in, you spin it in the centrifuge, and all the the platelets go to the bottom of the tube. That's a fictitious force that pushes them that direction, which is kind of funny. But fictitious forces do feel kind of real. Okay, so what are the forces that are real? These are the forces that are real. And you're not going to see the inertial force or the centrifugal or something like that on here. Gravity, that's real. Normal, tension, friction. And friction is divided into two things called kinetic friction and static friction. I always distinguish between those two because they're very different. There's a spring force, there's Hooke's law comes up sometimes. Electric force, magnetic force, these are more like from Physics 132 in January. So you're not going to do those this year, but Professor Harlow will. Thrust, sometimes like a rocket is pushed forward. Drag force, air resistance comes up sometimes. Muscle force, okay, so muscles do apply force on bones usually because they're attached to bones. Some of these have an equation that almost always applies. For example, gravity. Gravity is just m times g, almost always. Also, kinetic friction has an equation. It's mu times the normal force or something. Electric force actually has an equation, F equals, I think it's K Q1 Q2 over R squared or something like that. Anyway, normal force has no equation, tension doesn't have an equation, static friction doesn't have an equation, spring force does, I guess. It's Hooke's law, right? Times. Magnetic has an equation. These ones usually don't. But there's some handy ones that have a nice little equation associated with them and some that do not. And people are always turning, what's the equation for normal force? Well, there is no equation for normal force. It's whatever is needed to prevent the object from crashing through the surface. So let's talk about those. So for example, again, if I stand on the table, there's a normal force upwards on me. And you can even measure it if I stand on this bathroom scale, which now shows me that there's, oh dear. There's a upward force on me of, it says 210 pounds. Okay, I think it's my shoes already. All right, something's changed. Didn't say that before. It's sort of strange. Anyways, so what that is it's measured. There's a spring actually inside this scale, and it's measuring the upward normal force that is preventing me from crashing through the table. And if I were to remove that force, I would accelerate downwards, right? Like this. Until I hit. So you remove the upward normal force, now there's an unbalanced force of gravity which makes me accelerate downwards until something else stops me from doing that. The table, or the scale in this case, exerts an upward force on Harlow. Here's me water skiing at Payette Lake in Idaho, where my mom lives. But the rope exerts a force on Harlow pulling me along there. Tension, and that's a tension force, okay, because ropes do this tension. Okay, good. Gravity, and as we pointed out, one very clever student, it's the Earth on Angry Bird, okay, exerts a force on an angry bird. So if you imagine an angry bird that's just kind of, it's got its wings tucked in, and it's just flying through the air, there's a force on it of gravity always acting downwards, and that's the handy little equation, mg, where g is 9.8 newtons per kilogram down. That may be a different unit for you, but it's the same as meters per second squared. But this way, you take mass in kilograms, multiply it times 9.8 in newtons per kilogram, and you get the force of gravity in newtons. So I like to call it 9.8 newtons per kilogram. And then 9.80 to give it three significant figures, I guess. Sometimes you call this the weight. I don't know if it's really such a good name for it because it's a bit confusing, but anyway, there is a force of gravity of the Earth on the object which pulls downwards. You might call it the weight. It's sort of what's read here. There is no newtons on this scale. It's pounds and kilograms, which is not quite right. Should read newtons if it's an SI scale, which it isn't. That's okay. A pound can be converted to a newton. Okay, so this is what I just mentioned. Gravity for Earthlings. So that if you have an object, mass MO, we'll put it right here. This is the object. Then there's an attractive force between the object and the center of the Earth. And this is Earth, E. It has some radius, 6,370 kilometers. It has some mass, 5.97 times 10 to the 24 kilograms. Then if you're near that big object, you're going to have a gravitational force on you, which will always pull you towards the center of that object, which we call down. So if you're in Australia, then down is up, because you're on the opposite side of the center of the Earth. It's always towards the center. And kids get kind of confused about this. It is kind of confusing. Down is a local direction. Okay, I'm going to leave you with one last learning catalytics. We have a little bit of time. I have 4 minutes. So I'm going to work through this. But what I want you to do is think about this. I'm standing on the scale. This did say 185, like I swear. Okay. Let's just pretend that right now it says 185 pounds. And 2.2 pounds happens to be equal to 9.8 newtons. That's my conversion. So if I multiply that out, convert it around, I get, this means there's an 824 Newton force pushing upwards on me. Now, if I ride in an elevator, take my scale with me, put it down, and the elevator is accelerating upwards at 1.5 meters per second squared, what should the scale read? Is it still 824? Or is it more than 824, less than? So without doing any calculations, this is a trick for the term test, just look at the 5 answers, see if you can maybe rule out 4 of them, and just take a guess and go on to the next problem. It's a time-saving kind of trick there. And meanwhile, I'll work it out. So let's actually figure out the mass here. So let's draw a situation. Let's put the system as me. And I'll draw a force diagram. So the forces here are going to be this upward force, force of the spring on, let's call it, I don't know, me, and the force of the earth on me. And this one equals to 824 newtons. I'm going to define plus is up. And I'm going to say that the Newton's second law, the force equals m times a. And a is equal to plus 1.5 newtons per second squared. So we just say that the force of the spring on me, which is what we're trying to find, minus mg equals ma. That's Newton's second law. I'm going to solve for f of the scale on me equals m a plus mg. So I could just pull out the factor of m and do a plus g. Okay? And so whatever my mass was, which I think was 824, 824 divided by 9.8 was my mass, times 9.8, 9.8 plus 1.5. And I get 950 newtons. That's the force of the scale on me. It's larger than the downward force of gravity on me, and that is why I accelerate upwards along with the elevator. Sort of make sense? And I'll post these. So I don't know if you picked that, if you just sort of intuited that it would be bigger than 824, but not negative. Let me just read this one out to you. Farmer has a donkey. This is an old fable, okay? Every morning, the donkey pulls a wagon from the shed to the field. The donkey begins to take Physics 131 in the asynchronous section, so you can do it in the evenings. One morning, the donkey refuses to pull the wagon. So the farmer says, "What's wrong? You always pull this wagon." And the donkey says, "Professor Harlow says, according to Newton's third law, if I exert a forward force on the wagon will exert an equal magnitude force backwards on me. Therefore, I can never accelerate the wagon." So think about that, and we'll talk about the flaw in the donkey's reasoning on Friday. See you then.